Good afternoon. I'm Jack Gertner. I manage the underfloor air business for Johnson Controls based in Long Beach, California. And for today's session, I'd just like to take about 12 to 15 minutes to give you an overview of kind of what's going on in the industry for underfloor air, and there's a lot of new stuff. And we're going to particularly focus on this new publication, just happen to have a copy, of the new ASHRAE Underfloor Air Design Guide. This has been 5 years in the making, and a collective effort by all of our industry partners, including our worthy competitors, access floor manufacturers, fabric duct manufacturers, to come up with some real industry lessons learned and really some new research and ideas about how we can build these better and continue to grow the marketplace for underfloor air. So with no further ado, what I'd like to do is just share with you some sort of macro numbers of kind of what's going on with the marketplace, how much of this is there out there, and in a declining construction start market, as you see here back through the last decade. You can see here in terms of adoption of raised access floor, penetration of the buildings, we're now at in excess of 20% of the buildings, meaning buildings in the commercial, industrial type, institutional type marketplace. That means 24% of those buildings have a floor, a raised floor. And of that 24%, this is really the big delta, is 70% now have underfloor air, versus when we got in the business in 1998, about 3% of the buildings had a floor, of which maybe 10% had the air, and that was typically in the data center world. So this 70% is a big change in the marketplace and a lot of traction for underfloor air across the board. This is the book, as I mentioned, and we have had 10 years of knowledge and new information about underfloor that's captured here. Is this perfect? No, but it's an interesting compendium that covers all the issues in making a successful underfloor air job, such as how you design it, how you build it, how you even maintain it. But if you look at underfloor air issues, and every job has not been perfect, every time we build one we learn, but time and time again the issues are, how do I maintain plenum integrity? How do I maintain air tightness under that access floor? How do I control it all? And most importantly, how do I maintain consistent temperatures across large floor plates so we have comfortable system? At the end of the day, that's what we're all about, is giving a better comfort level to the occupants. And that's what this really focuses on. Now just generally inside it, and we don't have time today to go through all the different design options, but there's roughly about 15 different system designs that are featured in this book with these types of schematics, and what you're looking at here is a cut through the building, highlighting really the perimeter, which is to my left, not so much the cores. The cores of these buildings pretty much take care of themselves from a cooling and heating standpoint, whether it's in Juneau, Alaska, or Milwaukee, or Philadelphia, they're pretty much going to be the same. This is where the rubber meets the road, at the perimeter. So all these design schematics really focus there, and again, we've got about 12 or 15, which is not to say that that's a be-all and end-all. One of the changes in this marketplace has been, versus a product or a system in a box, it's gone much more towards looking at a kit of parts that really focuses more on what that client, what that engineer, what the contractor involved has in mind in terms of a budget, in terms of a design preference. So more and more the jobs are becoming very different, one to the next, to solve a specific site issue. This one is basically showing an underfloor fan box rated only for heat, and what this shows is really a perimeter system that utilizes ducted, and it could be fabric or it could be sheet metal duct, to diffusers that in cooling mode, these diffusers are just using cool plenum air. But if it goes to heat, if this stat up on the wall says I need heat, these boxes will close to that plenum air. This fan only kicks on, and this interior box becomes like a return grill. So it starts to pull warmer space air out to the perimeter, and that's the first stage of heat, and that could satisfy everybody, and we go back to cooling. If not, a second stage of heat can kick on, and we go back to adding heat until it's satisfied. A couple of lessons here just in terms of underfloor dynamics is that one thing we want to do as good, sustainable, energy efficient people is not to reheat. So what we're doing here is using space air as our first stage of heat. So my delta is going to be less. This air is typically about 62 or 63. My space air is more like 75, so now I'm reheating warmer air. So I'm being efficient that way. Supplemental fan energy, this only runs in heat. It's only rated at heat. Most of the time the only fan running is back in my air handling units. So I'm being efficient that way. The other learning here in terms of how do I maintain, how do I live with these buildings? With an underfloor system, it's quite different than an overhead ducted system. Overhead ducted systems, if you came in the morning as a contractor, how do I do early morning warm-ups? What you normally do is you'd put hot air into those ducts. Here, if we did that, if I took 90 degree or 100 degree air and put it under that floor, with all this mass in the subfloor, it would take a long time to heat it and then a long time to cool it back, so the building could start to yo-yo. So normally we want to just keep this consistent, rifle shoot in heat where you need it, like perimeters, like you see here. That's one of about a dozen which are highlighted in that guide. And one change that we've seen is this change versus that assisted fan-powered box you saw in the prior slide, which does require some ducting. It's stuff under the floor, if you will. It could be some obstacles, and remembering that our whole design paradigm is maintaining a flexible space. So in this case, what we've seen a shift away from fan-powered boxes to radiant type products, which you see here, which is essentially a sheet metal box with a radiant element in it. It could be heat, could be electric or hydronic, and in most cases, even with perimeters with floor-to-ceiling glass, we can handle that cooling load very nicely with radiant products. These could be heating and cooling with or without VAV. And our friends at ASHRAE and CBE up at Berkeley have also said that we're also paying about a 5% energy penalty to use these fan-powered boxes, especially if you designed a system, which some do, where you're using a cooling and heating fan, which would be sized for both cooling and heating loads, which would run 24/7. So we're seeing a real shift to these kind of devices, and we're showing one with heating and cooling and VAV with these devices. So a real shift to this, and the other part of the equation here are architects. Architects count, and what architects often like is this nice clean line at a perimeter wall versus a series of round or square diffusers. So our business has probably shifted to better than 50% using that solution. One of the largest platinum jobs in the country is a job for Wellmark out in Des Moines, Iowa, all with that kind of a system on it. So that's a big change. One other big change that's also reflected in our guidebook is a change to ASHRAE's ventilation effectiveness rating for underfloor air. For a long time, ASHRAE would only give underfloor a 1.0 ventilation effectiveness. They gave pure displacement a 1.2. Now, what that means is if we can get a 1.2 VE, that makes a case for 20% less need for outside air for the building. And the way we get that VE of 1.2, ventilation effectiveness, is that the diffusers have to be designed in such a way that at 4.5 feet throw off the floor, the velocity of the air has got to be 50 feet or less. And most diffusers in the industry, certainly all Army diffusers, meet that criteria. So that's a big change. It might not seem like a big one, but it's a really big change for the engineers. So 1.2 has changed, it's also reflected in the book. But this is what I mentioned earlier, which is this whole thought of how do we control temperature under the floor. A good rule of thumb, and still a good rule of thumb, is that from where the air enters the plenum, or the underfloor air handling space, to the furthest diffuser in that space, we want to maintain no more than about a 3-degree rise in temperature. That typically will equate to a comfortable space. If you get into 5, 6, 7, we've seen 10-degree changes, that is a problem in terms of just pure comfort. Case in point, this is a CFD model done for us by Flack and Kurtz. This was done 10 years ago. So 10 years ago, when we were thinking about modeling underfloor, it looked something like this. And what is right about this is we've got this rifle duct pushing cool air out to the perimeter. And that's what we should do, period. We're showing cool air being injected into the cores, not necessary. That can lead to an overcooled building. So the idea, the one we really missed was out here. Guess who sits in the corner office? The guy writing your paycheck. So we would normally not recommend that. Today we would look at something more like this, so that we're shooting air, again, cold air out to the perimeter. Once it gets to the perimeter, it's going to migrate back to the cores, warmer. It's going to pick up some heat as it goes back. But I'm treating my perimeter correctly with cooler air, keeping my cores relatively comfortable at the same time. So that's methodologies, there's lots of ways to do that, but that's the core idea, is to get the cold air where you need it, typically the perimeter. And to that point, again, early days in underfloor air, people were thinking, just throw the cold air out there, it'll migrate out and everybody will be happy. But once you start getting past the 50 feet, that can really gain some load, and we're showing here air coming in here, and if we just let it kind of scoot out there, it's going to gain some decent temperatures. Versus doing one approach here is to use in this case we're showing a fabric duct, can also be sheet metal or multiple sheet metal duct, to get the air out to the perimeter. And in the case of a fabric duct, of course, we can shoot it right to here, or we can put perforations and actually disperse the air nice and evenly at the end of that duct. So that makes a lot of sense, and there's been a lot of research done on that. It's also reflected in the new ASHRAE guide. Other approaches could be multiple injection points in a floor plate to help us get that air out there, or multiple air handlers, floor by floor, so lots of ways to skin the cat. But the idea, again, maintain consistent temperature, cool air to the perimeter, is the basic idea. And this is just a model of kind of what I'm talking about, and where we'd be, again, cool air out here, and we call it a reverse series, so that it goes out here, and then again, it's going to migrate back into that core. Warmer here where you want it, because we see too many, especially too many lightly loaded buildings versus what they were designed for, with cooler cores. That's when you see people throwing phone books on diffusers. We don't like that. One other thing, another kind of new thought, as terms of another methodology to get that cool air out there, is to increase the velocity of the leaving air at the duct, at the end of that duct. Because traditionally we've thought in terms of maybe 1,200 to 1,500 feet a minute. That's been textbook, and that comes from our overhead friends. Thinking, hey, if I get above that, I'm going to have noise issues with a high pressure static. Here we got low pressure, so we've run some tests, it's also in the book, where we can show that we can up that ante from 15, think more like 2,000 to 3,000 feet, and still maintain an NC of 35 at the end of the duct, and we've tested that on real world conditions. So we just suggest higher velocities. Higher velocities going to be okay acoustically, and it's going to really help us get that cool air out to the perimeter where we need it. Another thing that we're paying more attention to is return air paths, choke points, pinch points. And we're seeing more and more of that, and I'm not sure exactly why, but I think people are taking more advantage of the height issue at the ceiling, because we can get away with narrower ceilings with an underfloor system. But because we're using these low pressure systems, you have to get our engineers and our owners and building people to think larger return air paths, especially larger return grills in the ceiling. And these are just some rules of thumb that we typically size for now. No more than about 100 feet a minute velocity here, so larger than you're used to. You're probably used to more like 400 or 500. At my cross grills here, I'm going to be looking at maybe 200 feet here at the ceiling over here, and maybe 500 back at the shaft, but just basically larger return air pass. And oftentimes you walk into a room where they're saying it's stuffy. It's not down here the issue is, it's up here in the ceiling. So that's a kind of a big mental shift for a lot of us in the industry as well. And this just shows that the way we would do it would be normally, you want to have your return grills close to the perimeter, as high as you can get them, so that we're getting it up and out versus getting it mixed into the space. So that's visually what we're trying to do. Keep them up high, or we can either put a larger return air grill or take the ceiling and just touch it back from the perimeter wall, leaving a gap, which helps us there too. So again, a change up in how we think about return air. This is probably one of the most important lessons all of us in the industry live with each and every job. It's not rocket science, it's what we call constructability issues. How do we maintain the integrity of that plenum? And this is not building a submarine, but relatively tight, just good construction practice. And speaking for Johnson Controls, what we normally do, and almost every proposal, is have our own guys come out as man hours on a job, starting with meeting number one, which is all the trades on the job, not just the mechanical guy. We want the mechanicals for sure, we want the generals, we want building owner representation, we want the IT guy for sure, because every time they punch through a wall, they're making a hole, we have to seal it. If you make a hole, you seal the hole. So again, not rocket science, but more and more, just some poster child, here's a column, and if we didn't seal that column here, the plenum air would get into the column, and now I have a conditioned column and not a conditioned space. The stat would read the column, so now it's saying, I need heat in August and Houston. So that's what we try to watch for, and it could be anywhere. Here's a little entering duct, just a little sealant there. We like these guys to talk to, the actual mechanics doing the job. We could have guys with neckties and tell them all this at a meeting, but it's the guys out on the field that really make it happen for us. So we really believe in that, and the more we can do that, the more we can assure ourselves that we're going to have a good working job. And there's some excellent stuff in that book on these constructability detailing issues. Also our raised access floor friends at Tate Access Floors in Hayworth, who are basically the bulk of the market for raised floors, they also have some excellent stuff on their websites that highlight this. So that's it in a nutshell. We're excited about the growth in underfloor air. And I was talking to a gentleman earlier and says, where is this stuff? Well, it's pretty ubiquitous. And actually one of the larger jobs now considering underfloor air is the new Apple headquarter building up in Cupertino. And that's all displacement underfloor air. So if Apple likes it, we like it. Well, ladies and gentlemen, thank you for your time. I really appreciate it. Thanks for listening.